Hello all, so let us continue, and sorry for the abrupt stop in the video. Okay, it because of this technical fault. I don't know. So let me discuss the last point again. So if the interatomic distance is of this order, that is OQ, then what will happen? This crystal will behave like semiconductor. That is, this distance belongs to a, a semiconductor. Okay, and so and this crystal and the electrons in this crystal have energies like 1s2, then 2s2, then 2p6 between EC and E top and between EV and E bottom. But it cannot have energy in between these two, that is EC and EV, that is between forbidden within the forbidden gap. Okay, so even if you try, one more point is that even if you try to inject electrons inside silicon having energy between EC and EV, that is, suppose someone is interested in that injecting the electrons having energy EC and EV, then what will happen? Then this silicon crystal will reject them. That is, it is the property of nature. Okay, and over here, to be specific, we can say these are the rules of quantum mechanics. Clear? So all this thing of called quantum mechanics. So even if you try, it will not accept. So your try will fail. Clear? Now what happens if this interatomic distance is OP? That is, P is the point over here. That is, the EC and EV are overlapping over here. And we all know when the overlapping happens, we know it is a metal. So if the interatomic distance is of the order of OP, then the crystal will behave like metal because the EC and EV over here are overlapping. Clear? So this belongs to metal. And let's consider some another point R very far inside, that is interatomic distance is very small. So what happens over here, the band gap will be very much large, and so what we can say that it behaves like insulator. So let me write, this is insulator, this was semiconductor, and this is metal. Here now let's discuss some points based on this. So some points to think. Okay, now very first question is, let me take this page in parallel with this. So first point is that it means that is it possible that if we compress the metal, okay, as we all know this is interatomic distance, so we know the compressive stress and tensile stress from last video. So if we compress, then the interatomic distance will decrease, and then we can say that from metal we are moving towards insulator. So if we compress metal very much hard, then it becomes insulator. So is it really possible? So first of all, let me write the point that is it possible that if we compress metal so that interatomic distance decrease and thus it becomes insulator? So answer is no. And why? The reason is you have to put infinite energy. Okay, because the interatomic bonds are so strong that we can't imagine. Okay, now another question is that what actually decides this distance? That is, this distance of order OQ belongs to semiconductor. This distance of order OP decides the metal. This distance of order OR decides the insulator. So it is all being decided by property of nucleus. So different, obviously we all know that different crystals have different nucleus properties. So all this is being decided by nucleus property. Okay, so property of nucleus. Okay. So some nucleus with particular number of protons will settle at this Q point and we call it semiconductor. Similarly, some nucleus with particular number of protons settle at point P and we can say it is a metal. And similarly, some nucleus, okay, with particular number of protons will settle at point R, and we can say it is insulator. So now let's discuss some dependency on temperature. So band gap what happens to band gap when temperature is increased? So if we increase the temperature, then what happens to band gap? That is our forbidden gap. So if the temperature is increased, then what happens? Obviously, the interatomic distance will increase, and so the band gap will decrease. I hope it is clear. Now, effect of adding impurities. So as we all know that as we add impurity, so another question is, if impurity is increased, so what happens? As we all know that impurity is increased, then interatomic distance will increase, and so obviously band gap will decrease because less amount of energy is needed to break that bond, and that's the reason why band gap decrease. So interatomic distance will increase, and so band gap will decrease. Now let's plot some energy band diagrams. Okay. So first of all, consider the semiconductor silicon crystal. Now we are specifying silicon crystal. Energy band diagram of silicon crystal. So we are not giving any supply. Okay, no biasing, nothing. So just simply we know we have the allowed energy states are this. Suppose this is E top and this is EC, and similarly this is EV and this is E bottom, and this is forbidden gap. Clear? So, and obviously we have to specify if we need 1s2 and 2s2 and 2p6. Okay, so energy band diagrams are nothing but the energy, it shows the energy states possessed by the electrons in that particular crystal. So in silicon crystal, as we all know, the silicon crystal will have energy states like either 1s2, 2s2, 2p6, or in between EC and E bottom, or in between E top and EC, but it will not have energy states in between, so it is not highlighted. Clear? So we can draw energy band diagrams like this, but in actual practice, what we do, we draw like this. This is E top, this is EC, and this is EV, and this is E bottom. And this is our conduction band. Whole band is forming conduction band. This whole band is valence band, and this is our forbidden gap EG. So here x-axis has no meaning. Just to visualize that this is you can say that there is a drawback visualizing in this diagram because someone may get confused that what is this drawn. Just we have highlighted this portions. So that's the reason why we do this, and we actually draw like this, and this is our conduction band, this is our valence band, and this is our band gap. Okay, so please note that no x-axis. X-axis has no meaning in energy band diagrams unless they are specifying. Suppose they have specified that suppose the doping case is of non-uniform doping, then we will deal later on about non-uniform doping. But yeah, this is one of the examples where the x-axis will be preferred. Okay. Now we will be discussing imperfections in semiconductors, and we will see now what are the recombination centers in a crystal. So stay tuned for next video.